behind in that. Okay, here's the problem. A 50 kilogram cannonball is shot from a cannon at Earth's surface to a height of 425 meters high, as shown in the picture. What is the gravitational potential energy as measured from the ground at the 425 meter height? So you always have to say where you're measuring the height from, and usually it's just the ground, but it could be like a tabletop or something depending on the problem. The cannonball then falls to a height of 225 meters. What is the change in potential energy from the 425 meter height? Okay, so here's what's given. And you're also given that the mass is 50 kilograms. You do need to know the mass in this problem. Okay, and so for part A, so here's what we're trying to find. We're trying to find the gravitational potential energy. And I'll just put a little 1 right here. I like to show, where things are with little numbers, so we'll just put U sub G sub 1. You didn't have to do that, okay? It's just my way of keeping track of things. And then when we're down here, I want to find, delta Y. Not delta Y, hold on a second. Delta U sub G, going from here to here. So let's solve it. Let me zoom out so you can see the whole paper here. Okay, so for part A, let's solve it. Okay, U sub G is equal to mgh. We know this is 50 kilograms. This is 9.8 newtons per kilogram. And the H is 425 meters. And Saber, this is for you. So let's see if we can squeeze that in there. 425 meters. Okay. So, so it's quite a lot of energy, isn't it? So U sub G is equal to, what do you get when you multiply 50 times that? So that's like 500, 200 what? 208,000 joules. Is that correct? Everybody agree with that? 2008?
Sorry, 208,250.
Yeah, I think they just rounded it off, huh? So I'll accept either answer, but you really should round off stuff, because if you are putting digits here, significant figures right there, it's phony. You don't really know it. I mean, look, these are all 2 significant figures. You don't really know it beyond 3 significant figures. Yes?
So you're telling us not to be accurate.
I'm telling you to not lie. Because if you put 208, and then what did you have here when you on your calculator? What? 250. This is, your level of certainty is maybe 3 significant figures here. So if you put in 5 significant figures, you're implying a precision you don't have. The uncertainty here is within, maybe 1%. If you have it all the way out here, you're like 1/1000th of 1%. Now, it's not that big a deal. I don't make a big deal out of significant figures, but this is really much more truthful. It's not as precise, but it's more truthful than this. Okay, well, that's for part A. Now, for part B, what you really have to go realize here is that this is a change in potential energy. So you have to go delta U, and that's going to be equal to U final minus U initial. Okay? And U final is mgh final minus mgh initial. Now, you didn't have to show your work exactly the way I'm doing here. I'm just kind of showing you. This is mg h final minus h initial, right? Whenever you have a delta, you have final minus initial. Well, now I can plug in my heights. Well, this is 50 kilograms times 9.8 newtons of force per kilogram of mass. And you could use meters per second squared, I don't care. And then, well, what is H final? 225 meters minus 425 meters, right? That's H final minus H initial. And when you do the calculations, what do you get? Negative 98,000 joules. Okay? Or, I mean, some of you probably put some digits in here. What digits do you get if you keep them? Oh, really? It's that good. No. You really don't know what you're talking about. All right, but that's okay. So delta U, now it had to be negative, right? Because your final height is less than your initial height to figure out the change in potential energy. And so there you go. That's how you do that particular problem. So let's zoom all the way out. I think I am. Now, what's the big deal here? The big deal is gravitational potential energy is the work that gravity can do if you release it. So, look, you shot a cannonball up here. Where did the energy come from? It came from the chemicals in the gunpowder, releasing that energy, pushing the ball up, did work on the ball. That work became kinetic energy. As gravity slowed it down, we transferred energy from kinetic into potential energy. And we know that the equation that describes gravitational potential energy is mgh. So we plug it in there, you get there. The other big deal for part B is whenever a problem asks for a change in something, that's a final minus initial. And it is possible to have a negative change in energy. Okay, that is, we lost gravitational potential energy. Where did that lost energy go? Well, it could be into the environment. There might be a little bit of air friction, but we're going to neglect air friction in this case. It became kinetic energy, right? The cannonball is falling down really fast. Okay, so there you go. Any last questions?